Today we're going to take a look at the third part of Module 3, and this is still dealing with our probability distributions. And the last time we met, we talked about the binomial probability distribution. We also went through the normal probability distribution, and I'm going to bring up the calculator here. Right. And as far as the calculator is concerned, okay, we were in distribution. Actually, let me reset the calculator. All right, we were in this distribution function. We looked at the binomial PDF, the binomial CDF. So again, the binomial PDF is the binomial probability distribution function to find exact values. The binomial CDF, or the binomial cumulative distribution function, is used to find probabilities at that value and less. We also had taken a look at the normal CDF. Okay, and with the normal CDF, we can actually specify a range, and it works differently than the binomial CDF. So today we're going to continue on with the normal CDF. So just remember there's 4 requirements for the normal CDF. There's a lower limit, an upper limit, a mean, and the standard deviation. And we're going to evolve from a sample distribution to a sampling distribution. Now here is the difference between a sample distribution and a sampling distribution. A sample distribution takes a singular sample from a population. A sampling distribution is a distribution of a statistic from multiple random samples. Now, as far as going through the problems, here is the actual difference. Well, let's see. If I go back to the handouts, and so if I just go back to the last lesson, Module 3, Part 2, and you'll notice in these problems, when you're asked for probability, it says if you randomly purchase one item. So in this particular problem, this is a singular sample. If we take a look at the next problem, it says find the probability that the height of a randomly selected tree. Okay, so these are single samples which use a sample distribution. In this particular module, in this particular section, we're going to look at a sampling distribution, and you're going to notice the construct of the problems are going to change. Instead of randomly selecting one item, you're going to randomly select multiple items, right? For example, I'm going to go back to, or actually go forward. If we take a look at the next handout for Module 3, Part 3, you notice that these questions are a little bit different. Question number 1 says a population of values has a normal distribution with a mean of 243.2 and a standard deviation of 48.9. You intend to draw a random sample of 35 items. So notice we're sampling more than one item. Whenever you sample multiple items, this would constitute a sampling distribution. Okay. So you also notice on the second one, it says a random sample of 64 unemployed individuals, okay, were sampled. So these problems consist of what's called a sampling distribution. Okay, now to talk more about a sampling distribution, the main objective of a sampling distribution of a statistic it's a distribution of which all values of that statistic in which all possible sample sizes are taken from the population. And just the definition of a sampling distribution of a statistic, it's a distribution of values of the statistic when all possible sample sizes of n are taken at the same population. So this would constitute a new set of formulas, right? So I'm going to write the formulas for the sampling distribution. And so the only difference is we're going to introduce an n parameter. So for a sampling distribution, we have the mean, right? And the mean is written out as mu sub x. And that's just going to put colons here. And that's going to equal to mu, right, which is the mean. Next, we have the standard deviation. Right, and that's sigma sub x. So you're going to notice in the formula, you're going to see these subscripts of x, which indicates a sampling distribution. This is going to equal to the standard deviation divided by the square root of n. Right, so notice our mean stays the same, but the standard deviation, we must divide the standard deviation for that sample by the square root of n, where n is the sample size. Okay, because we're dealing with sample sizes that are larger than 1. Okay, so this constitute a sampling distribution. You will also asked to find the z-score of a sampling distribution. So that z-score is going to be x minus the mean divided by the standard deviation over the square root of n. All right, so our formula for the standard deviation changes and the formula for the z-score changes. All right, so we're going to look at a couple of problems. All right, so this is from the module 3, part 3 handout, and we're going to use the normal CDF just as we've been using, but the only difference is that when we put in the standard deviation, we must use the standard deviation formula for a sampling distribution. Okay. All right, so here's how all that works. Problem number 1 reads, a population of values has a normal distribution, right? So it does follow the empirical rule with a mean of 234.2 and a standard deviation of 48.9. You intend to draw a random sample of 35 items from the population. Find the probability, so remember that probability is area, that the mean of the sample is less than 260.6, and we want to round our answer to the nearest decimal. Okay, the nearest 3 decimals. All right, so I'm going to just draw a sketch of the problem. So we're given that it follows a normal distribution, right? So it's going to follow this bell-shaped curve. It has a mean of 234.2, and it has a standard deviation of 48.9, and N, which is our sample size, is going to equal to 35. All right. We're asked to find a probability that the mean of the sample is less than 260.6. Okay. So I'm going to guesstimate 260.6 right about here. And what we're asked to find is the area below 260.6, right? So just remember, for our normal curve, to the extreme left, we have negative infinity, which we represent in the calculator as negative e to the 99th power. To the far right, we have positive infinity, which we represent by e to the positive 99th power. And so we're going to set this up using that normal CDF function. So to find a probability that x is less than 260.6, this is going to equal to the normal CDF. We're going to put in the lower limit, which is negative infinity. So that's negative e to the 99th power. We're going to put in the upper limit, which is 260.6. We're going to put in the mean, which is 234.2. And since this is a sampling distribution, we're going to put in the standard deviation, but we're going to use this formula, right? So we're going to put in the standard deviation, which is 48.9 divided by the square root of n, which is 35. So we're changing up the formula for the standard deviation because we're dealing with a sampling distribution. All right, so we're going to calculate this. All right, so we're going to use that normal CDF function, negative e to the 99th power, that represents negative infinity, comma, 260.6. The mean is 234.2, and the standard deviation is 48.9 divided by the square root. So notice we're given a begin parenthesis. I'm going to put in 35. I'm going to close the square root, and I'm going to close that CDF function. And let me check what I have. I have a beginning, okay, 234.2. Okay, I forgot my comma. Let me put that in again. So that is the normal CDF. Negative infinity, which is negative e to the 99th power, comma, 260.6, comma, and I believe I hit the parenthesis instead of the comma. The mean is 234.2, comma. The standard deviation for the sampling distribution is 48.9 divided by the square root. So it gives me a begin parenthesis of 35. Close off the begin, close off the square root, close off my function. Okay, and we have 99.999. So we round that to 3 decimal places. This would equal to 0.999. So that's a 99.9% chance, which is highly likely, right, that the population mean would be less than 260.6. All right. So since we're randomly sampling 35 items instead of a single item, this constitutes a sampling distribution. All right, if we take a look at problem number 2. Okay. Assume that for the population of all unemployed individuals, the population mean length of unemployment is 37 weeks. And that the population standard deviation is 2.8 weeks. Suppose you would like to select a random sample of 64 unemployed individuals. So since we are sampling more than one individual, this would constitute a sampling distribution. We're asked to find the probability that the mean of the sample size is more than 37.3. All right, so I'm going to sketch the region. The question doesn't ask for this, but just to give a visual on what we're actually doing. All right, so the mean is 37 weeks. All right, so the mean is always located in the center of your normal distribution. The standard deviation is 2.8. N is 64. We're asked to find the probability that the mean of the sample size is more than 37.3. So I'm just going to guesstimate 37.3 right about here. And we want to find the area above 37.3. So here again on our normal curve, to the extreme left we have negative infinity. To the rightmost we have positive infinity. So we're going to use the normal CDF. We're going to find a probability that x is greater than 37 point, excuse me, that's 37.3. So this is going to equal to the normal CDF. We're going to put in the lower limit, which is 37.3. We're going to put in the upper limit, which is infinity, which is represented by e to the 99th power. We're going to put in the mean of 37. And we're going to put the standard deviation in as 2.8 divided by the square root of 64. All right, because we're using the standard deviation of a sampling distribution. So we're just going to put this into the calculator. So this is the normal CDF. The lower limit is 37.3. The upper limit is negative infinity, which is represented as e to the 99th power. We're going to put in the mean, which is 37. The standard deviation for the sampling distribution is 2.8 divided by the square root of 64 is 8. Right, so I'll just put in 8, close off my parenthesis, and we have 0.196 as the probability that the sample size is more than 37.3. All right, so that was the first two questions. Now the third question, it actually has multiple parts. And did I cover up something? Yes, I did. All right, there's actually 4 parts to this question. All right, so we're going to go through it. It says using, and you're given a lot of numbers here, but you're not using all of the numbers. So we're going to read through this one carefully. It says using all 1991 birth records in a computerized national birth certificate registry compiled by the NCHS, statistician Tracy Clemens and Marcelo Pagano found that the birth weights of babies in the United States are not symmetric, right? Are normal babies. The American statistician, in November 1999, 53:4. So that's where this information can be found. I'm assuming this is accurate information. It says, however, they also found that when infants born outside the typical 37 to 43 weeks and infants born to mothers with a history of diabetes are excluded. Okay, so they're taking some infants from 37 to 43 weeks out of this sample. The birth weights of the remaining infants do not follow a normal model. Excuse me. The remaining infants do follow a normal model with a mean of 3,432 grams, 3,432 grams, and a standard deviation of 482. The following question refers to infants born from 37 to 43 weeks whose mothers did not have a history of diabetes. So the first thing you want to ask yourself, is this a sample distribution or a sampling distribution? Well, if it were a sampling distribution, you would be given a random sample size. For this problem, we're not given a random sample size. We're given the mean, we're given the standard deviation. The 37 to 43 weeks, that's not a sample size. Those are just the infants born in these particular weeks. Okay, so this would actually be a sample distribution. Okay, so even though you see the words like infants, and then we see that an infant born or infants born between 37 to 43 weeks, this does not constitute a sampling distribution. This is a sample distribution. Because no sample size is given. Okay, so even though this question is in the sampling distribution section, it's not an actual sample distribution. So I'm going to sketch out this region. So it says that infants born between 37 and 43 weeks do follow a normal distribution. The mean weight of the babies is 3,432 grams. So 3,432 is the mean. The standard deviation is 482. Okay, no sample size of N is given. All right, so we have an A, a B, a C, and a D. Okay, this is actually broken down into 4 parts. A says compute the Z-score of an infant who weighs 3,980 grams. Round your answer to at least 2 decimal places. All right, so for A, just remember that the Z-score for a sample distribution, that's equal to X minus the mean divided by the standard deviation. So in this z-score formula, we're going to substitute x for 3,980. We're going to substitute the mean for 3,432. And we're going to substitute the standard deviation for 482. All right, so substituting all that into the formula, we have 3,980 minus 3,432 divided by 482. Right, so I'm going to simply just put that in the calculator. However, I'm going to put a set of parentheses about the numerator, right? So to force the calculator to perform the order operations. So this is 3,980 minus 3,432. I'm going to close off my numerator. Divided by 482. And we have a z-score of 1.14. So that means if we were to convert the 3432 into a standardized z-score, that would represent 1.14. All right, B says approximately what fraction of infants would you expect to have birth weights between 2,810 and 3,200 grams? All right, round to express your answer as a decimal and round to at least 3 decimal places. All right, so for B, we're going to use the normal CDF function. So I'm going to sketch out that region as well. So this is for B. All right, so this follows a normal distribution. The mean is 3,482. We want to find what fraction, what probability of what area is in between 2,810. So I'm just kind of guesstimating on my curve. So I'm going to guesstimate 2,810 about here. And 3,200. So I'm going to guesstimate that about here. And I want to find the area between these two values. All right, so we're just going to use that normal CDF function. So to write this out, we want the probability that Right? So remember that area is probability. All right, if we take a look at C. C says approximately what fraction of infants would you expect to have birth weights above 3,200? Express the answer as a decimal rounded to 3 decimal places. All right, so I'm going to sketch out this region as well. So we want birth weights above 3,200. So this is C. All right, so it follows a normal distribution. The mean is 34. 32. Right, that's our mean. The standard deviation is 482. We want the probability or the area for infants with birth weights above 3,200. All right, so I'm going to just guesstimate 3,200 right here. All right, and we want the area above. So remember, on our normal distribution, to the far left is negative infinity, to the far right is positive infinity. So if we put this into our calculator, the probability that x is greater than 3,200, that's going to equal to the normal CDF. Our lower limit is 3,200. The upper limit is positive infinity, which we're going to represent as e to the 99th power. The mean is 3432, and the standard deviation is 482. All right, so this is the normal CDF, 3,200, comma, e to the 99th power. Well, I hit second and the comma, and that pulls up. It actually is EE on the calculator, okay. But when you actually hit the functions, it just appears as E, a single E.
And you just put the 99.
That's right.
Okay.
Right. So that represents positive infinity. Okay. Comma, the mean is 3432, and the standard deviation is 482. Right, and we get 0.685. So 0.685. Okay. All right. So the last question, it asks for something that's a little bit different. It says, a medical researcher wishes to study infants with high birth weights and seeks infants with birth weights among the heaviest 22% above what weight must an infant's birth weight be in order to be included in the study? All right. So I'm going to sketch out that region. So this is D. All right, so this follows a normal distribution. The mean is 3,432 grams. The standard deviation is 482. But what we want, remember that area is probability. And this says the heavy is 22%. So I'm actually given an area. So I'm going to guesstimate 22% of the heaviest. So I'm just going to take this. And I'm given that this should be 22%. So how can I find this X value? So it's like we're doing it in reverse. We were given the area, right? And if you're given an area, you can actually find a probability, right? Because a probability is area. But here we're given a probability, we want to find the X value. So I'm going to introduce a new function. It's called the inverse normal function.
So what's coming? So the 22%.
Right.
How do you decide?
Well,
yes, of the 34, 32 going that side, and it would be negative after going that way. So this way.
well, looking at the problem, it says the heavy is 22%. So that means that the 22% I'm looking for should be at the top end of those birth weights. Now, if it said like the lowest 22%, I would shade the lowest part of it. Right. That's right. So to find a value given an area, we use the inverse normal function. So now if we take a look at our problem, I'm not actually giving the area to the left. I'm giving the area to the what? To the right. The inverse normal function, it requires the area to the left. I can actually find the area to the left by subtracting, right, from 100%. So for this particular problem, I have to find the area to the left. So the first thing I'm going to do is find the area to the left.
So if it's giving me the area to the right, and you can select whether it's left, right, or center? Can you do that?
Well, we can't do that with the inverse normal. We can do it with the normal CDF function, but the inverse normal works differently because we got to put in 3 parameters versus 4 parameters. So the first thing I'm going to do is find the area to the left. So they give me the area to the right, which is 22%, right, which is 0.22 as a decimal. So to find the area to the left, I'm going to subtract 1 minus 0.22. And that's going to give me 0.78. Right? Because 0.78 would be the area to the left, right? So in my inverse normal function, so that's the first thing. If I'm not given the area to the left, I have to find it. So I wasn't given the area to the left, I was given the area to the right. So we found the area to the left by subtracting from 1. Now I'm going to use this inverse normal function. I have everything I need. So that's going to equal to the inverse norm. I have to put in the area to the left, which is 0.78. I have to put in the mean, which is 3,432. I have to put in the standard deviation, which is 482. And once I put that in, it should give me the birth weight of the babies. The heaviest 22% of the babies. So I have inverse normal, 0.78, comma 3432, comma 482. I'll put a parenthesis again. So let me do that over. So it's inverse normal, 0.78, comma 3432, comma 482. And we get 3,804 grams. So that means that the value for that area should be 3,804 grams.
That's that's a comment, because I guess in my calculator, it has those 3 parameters, but it gives me a
Oh, you got a 84?
It gives me a choice, and I just did it right, and it gave me the same answer you got. Let me go back to it. It gave me the same answer that you got. I did that, and it gave me.
Okay, yours is different, so you can just put in the area. Okay.
And then it just gave me that. That's why I was asking.
I got you. Okay.
If it's giving me right, then I can put it.
That's right.
But if it's not, I need to find the area that's supposed to.
That's right. Okay. Now this is an older model calculator, so the functions in that's the newest model you have, so that makes it even easier, so you don't have to do the 1 minus in yours. That's right. All right. So that was part 3. All right, so we're going to take a look at the last part 4. And part 4 is really just going through that inverse normal thing again in a little bit more detail. Because there's actually a section that is entitled the inverse normal section. Okay, so the slides are maybe a little bit out of order. I believe the very last section dealt with the sampling distribution stuff. And the section before, I believe it's 3.4, it deals with the inverse normal. But as far as the slides are concerned, we're doing the inverse normal last. All right. So what we just did was part 3. Yeah, that was part 3. That deals with this.
We have those problems in our.
Yes. Yeah.
Okay, part 3.
Now this might be a little bit misleading because the module 3 probability distribution, it says part 3, but it's actually part 4.
Okay.
The very last one. They're in order on the website. I just got to make some changes as far as the numbering.
Okay.
But this is that very last set of slides from, and this actually is supposed to be part 4.
Part 3 is part 4, where it says starts with sampling distribution.
Yeah, that sampling distribution, that's actually part 3.
Oh, mine said part 3.
Yeah, they both say part 3.
Mine, well, I think you already told us. Look
Right,
like I marked
right,
part 4 out. That's what it is.
That's right. Yeah, that should be part 4.
Right. Okay.
So the first slide on that part 4 should be talking about percentiles. Is that what you're?
Let's see, part 4.
Yeah, I believe that's it. Yeah, okay.
Uh-huh.
So when you talk about a percentile, we're basically talking about this inverse normal. So here's the definition of a percentile. It says the location of a score in a distribution expressed as a percentage of cases in a data set with scores equal to or below the score in question. Thus, if a score is said to be in the 90th percentile, this means that 90% of the scores in the distribution are equal to or lower than that score. So if you've taken like a standardized test like the SAT or the PSAT, when you get your score, it'll tell you that you're in the 80th percentile. This is actually what that means. Like the 80th percentile, what means that your score in the distribution, there are 80% scores that are equal to or lower than your score. Okay. So that's the definition of a percentile.
So you said when we were talking about percentile, we were talking about inverse norm.
That's right. Finding that,
Finding.
because you're taking that 90, you're taking that percent or that area, and you can actually convert that to a test score. All right. So the next definition, it gives you some examples of percentiles. So we've seen these things before. The first quartile, and the first quartile is the 25th percentile. It says that 25% are the values are equal to or lower than 25%, which means that 75% would be above that particular value. Q2 is the median. It's also known as the 50th percentile. And it's the median is like 50% of the scores are below, 50% of the scores are above, right? The third quartile is the 75th percentile. So that means that 75% of the scores are at or below your value and 25% lie above. Okay, so you can look at a quartile as a percentile. And on the slide, there is an example, right? It says that a distribution of values is normal with a mean of 224.4 and a standard deviation of 18.9. Find P97, right? And this notation that you see actually represents the percentile.
97.
That's the 97th percentile, right? So I'm going to sketch this out. So it says that the values are normal And I'm going to copy this over into OneNote really quick. All right, so I'm going to sketch out this area, and this is the example from the all right, so it says that the distribution of values is normal, so it follows this normal curve. The mean is 224.4. The standard deviation is 18.9, and we want the 97th percentile. So that means that this area should be 97%. So notice when you're given percentile, that's automatically below. So since my particular calculator only calculates below, I'm going to put this, since we're already given the area to the left, which is 97%, we're going to use that inverse normal function. And we're going to put in the area to the left, which is 0.97. We have to put in the mean, which is 224.4, and the standard deviation, which is 18.9. Right? So what this is going to give us is that value that separates the 97 bottom percent from the top 3%. So I'm going to put this in as inverse normal, 0.97, comma, 224.4, comma, 18.9. And we get 260. Right, we're going to round to the nearest whole number. And then there's a problem that's on the handout for number 4, and it's basically dealing with the same concept. And I thought I copied it over. All right, so we take a look at handout number 4. Just let me pull it up again. All right, so this is from handout number 4. And it's just only one question on here. And it's basically similar to the question that's on the example. It says a company produces steel rods. The length of the steel rods are normally distributed with a mean of 210.3 centimeters and a standard deviation of 1.8. Find the 49th percentile. Right, so here again, that percentile, that 49% would be that area to the left. Right. So in the calculator, we would just put in that inverse normal function. 3.49 is the area to the left. The mean is 210.3. And the standard deviation is 1.8. So now, since we're looking at the 49th percentile, that's almost 50%. So our value should be close to the mean. So we get 210.3. So notice we get like the same value, right? Because the 49th percentile is basically in the middle, right? Because you got 49 and then 50, which is the actual mean or the median. So that 49th percentile is close to the actual mean, right? So if we round, we in fact do get the same mean value, 210.3. Okay. And I want to take a look at the last problem, because normally there's some questions about this problem. In section 3.4, okay, so now like I alluded to, there's only 5 sections in chapter 3. 3.4 is actually the inverse normal section. But as far as the lecture notes are concerned, it's like the last part of the lecture notes. And in 3.5, it deals with that sampling distribution, right, which was before. As far as the lecture notes, this was actually part 3. Okay, so the slides are a little bit out of sequence as far as the homework problems are concerned. But if we take a look at section 3.4, and it is, I believe, the very last problem. Yeah, number 9. Okay, it says the number of chocolate chips in a popular brand of cookie is normally distributed, right? So this follows a bell-shaped curve with a mean of 19 chocolate chips per cookie and a standard deviation of 3.5. When the cookies come out of the oven, only the middle 90% in terms of the number of chocolate chips are acceptable. The rest are considered defective, all right? Because they would either have too less chocolate chips or they're going to have too many chocolate chips. So they want to cut out the cookies that have less than what they're supposed to have and the ones that have a whole lot more. What are the cutoff numbers for the number of chocolate chips in acceptable cookies? Okay. So we want the middle 90%. So I'm going to copy this over into all right, so this is 3.4, number 9. So we want the middle 90%. So I'm going to sketch this out. So it's normally distributed. The mean is 19. So they only want 19 chocolate chips in each cookie. Right? So that's the mean. The standard deviation is 3.5. So what 3.5 is, the standard deviation is, if you take 19 plus 3.5 and then 19 minus 3.5, The standard deviation is like the margin of error, basically. It's how far the chocolate chips stray from the mean. Okay. We want the middle 90%. So here's what that's going to look like. So if I want the middle 90%, so let's just say, for example, this is 90% in the middle. If there's a total of 100%, what is actually left? 10%, right? Because 90% plus 10% is 100%. I would have to take that 10%, I would actually have to break it up into two, right? So that means that this would be 5% and this would be 5%, right? Because altogether that would give me 100%. I want to find this value and this value. And I'm going to do that using the inverse normal function. Now, this is how this is going to work. In order for me to find this value, I can use the inverse normal, and I want to find 5%, right? Because this will be 5% of the chocolate chips are equal to or below. So to find this, or I should say this number, I'm going to use the inverse norm. The inverse normal for my calculator requires the area to the left of whatever value that I'm concerned with. So I'm concerned with this value. The area to the left is 5%, right? So my area to the left is 0.05, because I have to convert that percent to a decimal. The mean is 19, and the standard deviation is 3.5. So if I pop that into my calculator, that should give me the value. So that's inverse normal 0.05, comma 19, comma 3.5, and we get 13.2. So that means that if the cookies have less than 13.2 chocolate chips in them, we're going to throw them away, right? Now we also want to find that top 5%, right? Because we want to find out which cookies have more than that amount of chocolate chip. They're going to discard those, right? So to calculate this other value, my calculator only calculates the area to the left. So what I have to do is, first I have to find the area to the left. So I'm going to subtract 1 minus 0.05. So 1 minus 0.05, that should give me 0.95. So I want to use 0.95 in my calculation. So I'm going to put in inverse norm. I'm going to put in 0.95. I'm going to put in the mean, which is 19. Standard deviation, which is 3.5. So that's inverse norm 0.95, comma 19, comma 3.5. And we get 24.8. So that means if, and I guess in actuality we're round these because you couldn't have like 24.8. You'd have to have 25, but we're going to use the rounded values. So that means if you have more than 24.8 chocolate chips in a cookie, they're going to disregard those because that's too many. Right, so if we take a look at the, I'll just pop those in. So that's where the 13.2 and the 24.8 come in. There's usually questions about the last one. So kind of,
it would take the 13.2 and the 24.8.
yeah, the has between those amount of chocolate chips, they're going to package them up and sell them. But if they have less than 13.2 or more than 24.8, they're going to disregard.